Welcome to an exploration of the most extreme temperatures found within our solar system. From scorching infernos to frigid wastelands, the temperature variations across our cosmic neighborhood are truly astonishing. These extremes offer us incredible insights into the diverse environments that exist beyond Earth. Temperature itself is a fundamental measure. It quantifies the average kinetic energy of particles within a substance, indicating how vigorously they are vibrating or moving. In the vast expanse of space, several key factors determine the temperature of a celestial body. These include the amount of solar radiation a body receives from the sun. Additionally, its ability to reflect or absorb that energy, along with the presence or absence of an atmosphere, plays a crucial role in its thermal profile. At the heart of our solar system lies the undisputed champion of heat, the sun. This magnificent star is the primary engine driving temperature dynamics for every planet, moon, and asteroid that orbits it. Its immense energy output shapes the thermal landscape of our entire cosmic neighborhood. Deep within the sun's core, temperatures reach a staggering 15 million degrees Celsius, or about 27 million degrees Fahrenheit. This extreme heat is a direct result of nuclear fusion, where hydrogen atoms combine to form helium, releasing colossal amounts of energy in the process. This fundamental reaction powers our star. Moving outward from the core, the sun's visible surface, known as the photosphere, is still incredibly hot. Here, temperatures average around 5,500 degrees Celsius, or approximately 9,132 degrees Fahrenheit. It is from this surface that most of the sun's radiant energy embarks on its journey through space. Periodically, the sun unleashes powerful bursts of energy called solar flares. These energetic eruptions can briefly reach even higher temperatures, though these are localized events. The sun's intense heat and radiation are the foundational drivers of temperature throughout our solar system, influencing every object within its gravitational embrace. Mercury, the innermost planet, experiences perhaps the most extreme temperature swings in our solar system. Its proximity to the sun and lack of a significant atmosphere create a world of intense thermal contrasts. These conditions make it a true testament to solar influence. During its long day facing the sun, Mercury's surface can reach a scorching 430 degrees Celsius, or 800 degrees Fahrenheit. This temperature is hot enough to melt lead, showcasing the immense power of direct solar radiation. Any unshielded object would quickly succumb to such heat. However, without an atmosphere to trap and redistribute this heat, Mercury's night side tells a dramatically different story. As the planet rotates and faces away from the sun, temperatures plummet to a frigid 180 degrees Celsius, or 290 degrees Fahrenheit. This stark difference, a swing of over 600 degrees Celsius, highlights the critical role of an atmosphere in temperature regulation. The absence of a substantial atmosphere prevents any effective heat retention. It also means there is no mechanism to distribute heat evenly around the planet. This makes Mercury a world of extreme thermal dichotomy, an object of intense study for planetary scientists. Despite being further from the sun than Mercury, Venus holds the distinction of being the hottest planet on its surface. This counterintuitive fact points to a powerful atmospheric phenomenon at play. The conditions here are truly formidable and unforgiving. The primary cause of Venus's extreme heat is a runaway greenhouse effect. Its exceptionally thick atmosphere, composed almost entirely of carbon dioxide, acts like a dense blanket. This atmosphere efficiently traps solar radiation, preventing heat from escaping back into space. As a result, Venus maintains a constant surface temperature of around 475 degrees Celsius, or 887 degrees Fahrenheit, day and night. This temperature is hot enough to melt lead, making its surface an incredibly hostile environment. It is a stark reminder of what an out-of-control greenhouse effect can do. The dense atmosphere of Venus, also creates immense atmospheric pressure at its surface. This pressure is more than 90 times greater than Earth's sea level pressure, equivalent to being nearly a kilometer deep in Earth's oceans. These combined factors make Venus a true inferno. Mars, often referred to as the red planet, also experiences significant temperature variations, though not to the extremes of Mercury or Venus. Its thin atmosphere contributes to these noticeable fluctuations between day and night, and across seasons. This creates a dynamically changing environment. Near the equator, during the Martian day, temperatures can be relatively mild, reaching about 20 degrees Celsius, or 68 degrees Fahrenheit. This is warm enough for liquid water to exist, if atmospheric pressure allowed. Such conditions offer a brief respite from the general cold. However, once the sun sets, the thin Martian atmosphere cannot retain much heat. Temperatures quickly plummet to a frigid 100 degrees Celsius, or 148 degrees Fahrenheit. This rapid and dramatic drop showcases the atmosphere's inefficiency at thermal regulation. The polar regions of Mars are even colder, especially during their respective winters. Here, temperatures can fall to an extreme, 153 degrees Celsius, or 243 degrees Fahrenheit. This allows for the formation of significant ice caps made of both water ice and frozen carbon dioxide. Moving beyond the inner rocky planets, we encounter the gas giants, Jupiter, Saturn, Uranus, and Neptune. These colossal worlds present a different thermal environment altogether. They lack solid surfaces in the traditional sense, instead transitioning from gas to liquid at immense depths. For these giants, temperature generally decreases with altitude, especially in their upper atmospheres. Their great distance from the sun means they receive significantly reduced solar radiation compared to the inner planets. This factor contributes heavily to their overall frigid nature. While they do possess internal heat sources, especially Jupiter and Saturn, this heat is primarily radiated from their deep interiors. It does not significantly warm their upper cloud layers, which remain incredibly cold. Their vastness and composition define their thermal properties. Jupiter, the largest planet in our solar system, is a truly immense gas giant. Its upper atmosphere, observed through powerful telescopes and probes, hovers around 145 degrees Celsius, or 230 degrees Fahrenheit. This is a cold and turbulent realm of swirling clouds and powerful storms. Saturn, famous for its magnificent ring system, is situated even further from the Sun than Jupiter. Consequently, its upper atmosphere is even colder, typically around 178 degrees Celsius, or 288 degrees Fahrenheit. Both planets exhibit strong internal heat, but their vast scale and distance from the Sun keep their outer layers frozen. Uranus and Neptune, the ice giants, are the outermost planets in our solar system. They are often considered the coldest planets, with their atmospheres reaching truly extreme low temperatures. Their composition, dominated by water, ammonia, and methane ices, contributes to their frigid nature. Uranus has an average atmospheric temperature of around 224 degrees Celsius, or 371 degrees Fahrenheit. This planet is also known for its extreme axial tilt, which causes its poles to experience decades-long periods of continuous sunlight or darkness. Despite this, its overall atmospheric temperature remains remarkably uniform and cold. Neptune, while slightly further from the Sun than Uranus, surprisingly has an upper atmosphere that can be marginally warmer in some regions. Its average temperature is also around 224 degrees Celsius, or 371 degrees Fahrenheit. Scientists hypothesize that Neptune's slightly warmer atmosphere might be due to a more active internal heat source than Uranus. This internal energy drives the most powerful winds in the solar system. Beyond the planets themselves, our solar system's many moons offer their own incredible array of temperature extremes. Their proximity to their parent planets, internal activity, and atmospheric presence all contribute to unique thermal profiles. Each moon tells a different story. Io, one of Jupiter's Galilean moons, is the most volcanically active body in the solar system. Its constant eruptions and molten lava flows mean it experiences significant and rapid temperature variations across its surface. Hotspots can reach hundreds of degrees Celsius, while surrounding areas are much colder. Triton, Neptune's largest moon, is one of the coldest objects observed in the solar system. Its surface temperature plunges to an astonishing 235 degrees Celsius, or 391 degrees Fahrenheit. This extreme cold is a result of its distance from the sun and its highly reflective surface, which sends most solar energy back into space. Further out, in the distant reaches of our solar system, we encounter dwarf planets and countless other small bodies. These objects reside in environments where the sun's warmth is a mere whisper. Their temperatures reflect this extreme remoteness. Pluto, once considered the 9th planet, is a prime example. This distant dwarf planet typically has surface temperatures around 229 degrees Celsius, or 380 degrees Fahrenheit. Its thin nitrogen atmosphere can sublime and refreeze with its orbital journey, creating seasonal changes in its surface ice. Beyond Pluto lies the Kuiper Belt, a vast region of icy bodies. Even further still is the hypothesized Oort cloud, a spherical shell of comets enveloping our entire solar system. These regions are home to objects with temperatures that approach absolute zero, the theoretical point where all molecular motion ceases. Here, the sun is a mere distant star, and conditions are unimaginably cold. Our journey through the solar system reveals a place of truly remarkable temperature diversity. From the searing furnace of the sun's core to the almost absolute zero cold of the Oort cloud, the range is vast and awe-inspiring. Each celestial body presents its own unique thermal fingerprint. These incredible temperature variations are a testament to fundamental astrophysical principles. They are dictated by factors such as the amount of solar radiation received, the composition and density of a body's atmosphere, its ability to reflect or absorb energy, and the presence of any internal heat sources. Each element contributes to the thermal balance. Understanding these extreme temperatures is not merely an academic exercise. It is crucial for comprehending the formation and evolution of our solar system itself. Moreover, studying these varied thermal environments helps us assess the potential for life or for future human exploration, both within our solar system and beyond.